Yeah? Okay. Deal. We're the initial public offering. Bring pi.
Like how many percent per pi? That's what it is.
It's small percentage.
Yeah, like 1?
Like,
I think a percent.
yeah, like 1 per pi. 1% per pi.
So if it's like a better pi, you get more.
Is there a limit?
Is it like
No, actually, we go past 100%, in fact.
I started another.
Yeah.
like your fresh homemade apple pie is like 5%, but like Costco pie is like 1%. Is that like, you know? How
Something like that, yeah. Yeah. And like pies every day for a year, that's like 200%.
Yeah. Yeah. So every time you make $1, you owe us 2.
Something like that. Yeah. Okay, so lecture 6.2, proportional controller design. P. So P control. People don't usually call it P control, but we're going to call it PID control in a minute. So that's why we're going to use it. Okay, so proportional controller design is the task of choosing the gain K with which the closed loop system performs in a desirable manner. That's the goal of our design. All 3 performance classes, stability, transient response, and steady state error, can be affected by changes in the gain. That closed loop pole location is very important and affects all 3 of those categories. However, with the gain controller, there is typically no way to satisfy strict requirements in all categories. All we can do is move along the root locus, right? So we are limited to that. Typically, stability can be satisfied and transient response characteristics can be partially satisfied. Varying the gain simply moves the closed loop poles along the root locus. However, often the root locus does not pass through the closed loop pole location required for ideal transient response performance, which is a bummer. But later, i.e. next week, we will learn how to design controllers that do not have this limitation. Virtually always, we assume it is a requirement for the closed loop system to be stable. Therefore, we can immediately restrict our task to selecting from those values of gain for which the system is stable. So closed loop pole has got to be in the left half plane. That's going to be what stability tells us. Recall from chapter 3 the relationships between the location of closed loop poles and the corresponding transient response performance. Parameters such as rise time, peak time, settling time, and percent overshoot can all be related to the dominant closed loop pole locations. Criteria will be given in terms of these transient response performance parameters, and the design task will be to choose the best gain such that these requirements are met. For most problems, we make the first or second order assumption for higher order systems and for first and second order systems with zeros, even though it doesn't perfectly hold in many cases. Recall that even if this is an inaccurate assumption, it gives us a starting point for our design. We will always simulate to evaluate the actual performance criteria of a given design. So that's what we'll do. I mean, actual is relative here because second order approximation often doesn't hold very well. Simulation is pretty accurate, assuming your model is accurate, okay? The numerical solution is an estimate, in a sense, of what the solution is, but it's a very good estimate. But, as someone brought up in the earlier section of this class today, what about testing it in hardware, in the actual system? So, if your model of the system is really accurate, then your simulation should reflect the actual performance pretty well. But if you don't have a very accurate model, that's going to degrade the performance of your actual system as well. So, yeah. Good. But simulation's pretty good, and that's as far as we'll take it in this class. We're not going to actually take measurements of our actual controllers that we're going to implement. We're just going to be focused on the simulation part. The following procedure is one way to go about designing a proportional controller. Let us keep in mind the adage that plans are useless, but planning is essential. So, anybody who's wrote like a note card for their exam before knows this. You write your note card and then you like never look at it the whole exam, but if you never wrote the note card, it would have been a problem. So writing that note card tends to help you study for the exam. Okay, so here is the procedure. This is like a guideline to keep us honest, to keep us moving in the right direction for our design, but we can do different things as well. So 1, using the second or first order assumption, estimate the ideal location of closed loop poles for the desired transient response criteria. So you say, okay, you're given some performance requirements, and you're going to say, okay, I need a rise time of this, I need a settling time of that, I need a percent overshoot of this, I want it to be stable, etc. 2, construct a root locus plot and select the location on the root locus that is closest to the desired closed loop pole location. Using a computer, determine to which value of gain this location corresponds. So that's the MATLAB little data cursor that tells you what gain corresponds to that location on the root locus. 3, solve for the closed loop transfer function with this gain. Okay. And then 4, simulate the response for a unit step command. Evaluate the performance criteria and iterate if necessary. So that last step is going to tell us what's the sort of actual, or what's the simulated performance of this controller in closed loop. And it's going to give us access to answering questions like, what is the actual rise time? What is the settling time? What's the percent overshoot in this problem? And that's different than your second order approximation would give you. Okay, your second order approximation is probably inaccurate. So you get like an actual value, and then you have to tweak your gain accordingly. All right, let's do an example, shall we? Proportional controller design for percent overshoot. So for a plant with transfer function given below, design a unity feedback gain controller such that the system has a 20% overshoot and minimal settling time. So there's sort of 2 requirements here, 20% overshoot and minimal settling time. What does that correspond to? In terms of closed loop pole location. Let's think about that for just a moment. So if we draw our complex plane, percent overshoot of 20% corresponds to a specific damping ratio. A specific damping ratio has some constant line that starts at the origin and goes outward at some angle. That would be the 20% overshoot line. Okay? So every time there is this is corresponding to the second order approximation. So every time there is a second order system with complex conjugate poles and no zeros, if one of those poles shows up on that ray, the other one would show up down here, right? Symmetric about the real axis. You're going to have 20% overshoot exactly. But if it's only approximately second order, or it has zeros in it, then we're going to run into this being just an approximation. But we can start there, right? That can be our start. 20% overshoot line will be, we want to select a gain so that we end up being somewhere on that line. Also, we want to minimize the settling time, right? That was another requirement. Minimize the settling time. So if we're going to minimize the settling time, then we have to remember that in the complex plane, the settling time is going to get smaller and smaller as you move leftward, okay? More and more negative real parts of those dominant poles. So this is the sort of general idea that we get. This is sort of step 1 for our design. Where do we want our closed loop poles to be? Well, since we have a minimization question of like we want to move these as far leftward as possible but beyond that ray, we don't have a precise location that we want, but we just have like, okay, we know in general We want to be on that 20% overshoot line or close to it probably. And we want to be as leftward as possible. Okay. So now we got to look at the root locus, right? The root locus is going to tell us where we can actually get to on that line, what's actually possible. So using MATLAB to define the transfer function, using ZPK because we've already got the poles and zeros factored out here. Notice this is a second order system with 2 zeros. Okay, so good to keep that in mind. If it's a second order system with 2 zeros, will the second order approximation be, will it be just approximate or will it be precisely perfect? Remember, second order approximation is based on a second order system with no zeros. This system has 2 zeros, therefore it's just an approximation. All right, so let's take a look. So desired closed loop pools along this ray corresponding to 20% overshoot. Since this is available with the data cursor and the R locus plot, there is no need to compute the damping ratio or the angle of the ray. Let's consider the root locus. So you can just use the R locus command. Let's do that in MATLAB. So all right, so let's do a G equals ZPK of -13, -15, 2, -2, gain of 1. And then let's do figure R locus, and grid on is nice because then we get these lines of constant damping ratio and percent overshoot. And we also get these radial demarcations for natural frequency. Both of which, all of this is based on the second order approximation in terms of these grid lines, right? All that's the second order approximation. The root locus itself does not assume a second order approximation. It just is whatever it is. So you can put your data cursor on there. You can move it around. You can see, okay, to put my closed loop poles, put one of them there. I need a gain of 0.125, etc. We want a 20% overshoot, which you go from 0 here to 29.2% overshoot at that point. So we've got a big jump there. So, but there's going to be a crossover point at which we had 20% overshoot. But if you keep going, we're going to increase past 20% overshoot, and then we're going to come back to it. Okay, it's 22.4% overshoot there, 19% overshoot here. So between these 2 points somewhere is the 20% overshoot line that we're aiming for, right? So there are a couple ways to go about doing this. Probably we could just choose this gain of 19% overshoot, pretty close, and go from there. If you want to be a little bit more accurate, you can go back to this and put in some custom gains that are in the range of values there. And this is one way to go about sort of like putting in a bunch more points to use as your possible gain values. So that's something to play with if you're interested, but I just wanted to show you that as a possibility. Okay, so at the end of the day, though, we've got a gain of 0.032 to be on the percent overshoot line at this point, and then to be on the percent overshoot line at this point, 0.234. Since we have the second design requirement of decreasing the settling time, we want to move leftward as far as possible. So which of these should we shoot for? The more left one, so 0.234 being the gain that we want to shoot for then. So that's going to be the point that we start at for our design. It's based on the second order approximation, but that's a gain that is pretty solid. So let's go ahead and choose that. And then our step 3 in our design procedure is to test it out, see how it works for a step response. Find the closed loop transfer function and do the simulation. Well, you can find the closed loop transfer function and build it manually in MATLAB, which is totally fine. But MATLAB has this nice command called feedback. So if you come here and you say help feedback, it will show you that, if you have a transfer function in the forward path, which we do, our gain controller times the plant, and you have a transfer function in the reverse path, M2, which for us is just 1, just unity feedback, then you can find the closed loop transfer function by using this feedback command. Okay, so it's pretty straightforward. So all we need to do is say G closed loop equals feedback of the gain value that we want, so 0.234 was the gain value, times G, which is our plant, unity feedback, and there's our closed loop transfer function. MATLAB wants us to succeed. It knows that we're going to use it to do controller design, and so it's got tools in there that help us. So we didn't have to find, the closed loop transfer function being G over 1 plus G, which would also be totally fine, give you the same result. It didn't get the cancellation. These cancel. And then I believe it's the same. Something seems off, though. Is that not right? G over 1 plus G? That's the formula, right? For the closed loop transfer function? Anyways. I'm not sure what's up with that. It's a little bit off there. What's going on, guys? Oh! Because I didn't include my gain, right? So what I need to do is 0.234 G over 1 plus 0.234 G. There we go. Now we're good. If we canceled the poles and zeros, we would be equal to that one. So G closed loop using feedback is the same as using this kg over 1 plus kg. All right, so we're good. So we've got our closed loop transfer function, and now we're ready to do the step response. Okay, we need to simulate the step response. So we can use this step command. I used a final time in there because I didn't like the one that MATLAB just chose by default. It tries to figure out what a good one is, but doesn't always do something that you like. So what I'll tell you is, what? I think it was too short, yeah. I wanted it to go out further. So step, and then let's do G closed loop, and let's go out to 5 seconds. So now I've got my step response. And now we can do step info of y comma t. And it tells us the rise time, the settling time, percent overshoot, etc. So we're looking for a percent overshoot of 20. We got 24.5. It's a little high, right? It's because it's just an approximation, this 20% overshoot line. So we're going to have to adjust this gain. Looking back at our root locus, if we increase the gain, we're going to move back towards probably lower overshoot and also lower settling time. So increasing the gain is probably going to be good for us. So if we increase the gain, if we do gain of like 0.35, I mean, this could just be like, I iterated to get to 0.35. So you could do this a few times, right, and get to 0.35, and then do the step response again, and then do the step info again. And we got down to percent overshoot of like 19.7%. So we're pretty much right on the money. Close. You could probably iterate a little bit more and get closer to 20%. Oftentimes, you have like, you want it to be below something or above something. So like probably we want to be less than 20% overshoot. But we're pretty right on the money for overshoot now. So now we've got the overshoot that we want using this gain of 0.35. And our settling time is 1.07. We don't, I mean, if we keep increasing the gain, we'll keep decreasing the settling time, but we're going to move away from this percent overshoot value of 20%. So let's actually do that. Let's say you went up to 0.45. Then your step response, and then your step info, our settling time went down. So that was good, right? We want less settling time. We minimize that settling time. But notice that our percent overshoot's moving away from 20%. It's going down too. So probably going back to a gain of 0.35 is probably right where we want to be. That's probably, that meets our design requirements pretty well. And if we want to look at the step response, so let's do that. Let's actually do a figure plot t comma y. Turn on the grid. We see that there's a couple things that are interesting here. First of all, step response does not go to 1. Okay, command is 1, and it doesn't go to 1. So what are we going to call that difference here? Steady state error, right? That difference at the end here is steady state error. I mean, at infinity would be technically steady state error, but it's getting real close there towards the end, right? So steady state error is like, what's the data cursor say? 1.048. So the steady state error is like 0.048 here. And that's something that we would like to deal with. We can't deal with it, though, using just a proportional controller. A P controller will not give us a reduction in our steady state error. We're going to need to have an integrator that gets incorporated in. If we incorporate an integrator in, if we have a 1 over S term in our controller, we're going to be able to get that steady state error down to 0. But including an extra pole in our root locus, our open loop transfer function, and therefore our root locus, it messes with everything to do with the transient response. Like everything changes. The entire root locus changes. So what we're going to do in next week when we learn how to do PI control, proportional integral control, is we'll learn how to mitigate the effects on the transient response of putting in an integrator. So we'll talk more about that next week. But so we can't do anything about that. But our overshoot here is certainly, it's close to 20% because we don't go down to 0, or we don't go down to 1. So the steady state is not, or this is not a reflection of the complete percent overshoot. So this is probably about 20%, like we expected. And 19 is what the step info function gave us. So this is pretty good. But one way we can plot it is to divide by the steady state value, which is probably a good way to go. An easy way to do that is just divide by the last point in the Y array, which corresponds to that, right? That's the last point. So if you divide by that last point in Y, and you turn the grid on, then you normalize it by 1, and you see that the percent, or well, actually this was for the gain of a little bit bigger gain, wasn't it? We have only 16.9% overshoot. So let's go back to 0.35. make sure we do our simulation again. And then let's plot that and grid on. And we're right at 20%. So we're feeling pretty good about that design, I think, at this point. And looking at the step response, everything looks right. I don't completely trust the step info results unless I see the step response. Okay, so I would make sure you always check by looking at the plot of the step response that it seems about right. Okay, so yeah, I mean that was pretty much our design. We nailed our spec, and we also explored what happens if we keep increasing the gain and, well, we get away from one of our specs and we help the other spec. So this is a sort of design trade-off question that is hard to answer unless you have a real problem. So, okay, any questions, any, I guess, objections? Speak now or forever hold your peace now.
Nothing stops you from taking the output all of that data in a struct, right? Nothing stops you from just iterating through thousands of different games and just plotting all of the different responses, right?
Good. You're right. You're absolutely right. So one way to do this is to create a loop and try to do a minimization of your, say, the difference between the actual percent overshoot and the design percent overshoot of 20%. So they're going to be, so you can do like a minimization loop on it, and then stop when you get within like 0.5% or something like that. Whatever it is you want as your threshold. Nothing stopping you from doing that. I'll mention a couple points on that. So if you do that, you got to have a starting point. So what I would recommend, if you want to get real tight with your meeting your spec, you've got to keep in mind that there are two local minima here. There's going to be one that corresponds to the lower gain and one corresponds to the upper gain. So you want to probably do a sort of by hand process to get you to where you're at the right minima, and then do your loop from there. So if you really want to refine it down to like 5 digits of precision and get it down to like, 19.999% overshoot or something, then I would recommend starting out at a point that's close to where you want to be and iterating from there. Because otherwise you might find this minimum, and that is not what you're looking for, because you have this other design criterion, the settling time that you have to consider. So nothing stopping you. Step info is nice in that regard. Like you can just use it to just like go through the loop automatically. Yeah, feel free to do it. I think that it's you only need precision up to the level of accuracy of your model. So a lot of times our models are, they're going to be a few percent off. So getting to, 1/millionth in your design based on the simulation may or may not be of added value to you, depending on the system. Some systems are very well modeled, and it's a very complex system, and you're going to want to have a very accurate choice. But a lot of times, the gain choice that you make is going to only really be important within like 1% or 2%. Yeah, but you can, and I'm glad you're thinking like that. That's a good way to start approaching these problems. Like, how would I be able to like refine it? How could I use like a loop to refine it, which is really good. Any other questions? Okay.